Well, like you said, my presentation, I've prepared it in Swedish, so I will do it in Swedish, but hopefully, if you have any questions, you can ask them in English afterwards if you want to. Can everyone see the presentation all right? Is it in full screen and everything? Good.
Yes.
Perfect. Amazing. All right. Jag har jobbat med reglering av IFAS-processen på Nykvarnsverket i Linköping. Genom att först och främst utvärdera kvävereningen och sedan implementerat en överordnad styrstrategi på reningsverket. Så här ser reningsverket ut. Vatten kommer in från stan, det renas med mekaniska, biologiska och kemiska reningsprocesser och sen släpps ut i Stångån. Här är den biologiska reningen som består av 3 aktiv slamlinjer och sen en IFAS-process som är parallell med biosteg 3. Och de har även en MBBR-process, en Moving Bed Biofilm Reactor, som har biofilmsbärare i sig. Och jag har ju fokuserat mitt arbete på IFAS-processen. Och vad är då IFAS? Det är en kombination av aktivt slam där bakterierna lever fritt i slammet och MBBR, Moving Bed Biofilm Reactor, där man har biofilmsbärare. Så IFAS har alltså båda av de här 2 delarna. Vi har både aktivt slam och biofilmsbärare. Och namnet kommer från Integrated Fixed Film Activated Sludge, att vi har båda 2 av de här delarna. IFAS-processen på Nykvarnsverket driftsattes hösten 2023 och har styrts manuellt sedan dess genom att man har justerat syrebörvärde och flöde manuellt för att styra hur mycket nitrifikation som ska ske i processen. Och målet med mitt projekt var att implementera automatisk styrning av den här processen för att ersätta de här manuella justeringarna. Efter att jag då hade utvärderat den nuvarande kvävereningen, hur det såg ut på verket just nu, så behövde jag se hur systemet reagerade på förändringar för att se vilken typ av styrning som skulle passa systemet. Och då gjorde jag ett antal stegsvarsexperiment för att se hur systemet reagerade på de här förändringarna och för att kunna använda då för att trimma en regulator sen till slut. Här gjorde jag ett stegsvar i februari där syrebörvärdet, så det önskade värdet på syrehalten i IFAS-reaktorn, ökades från 4 till 5 mg per liter. Och det som man kan se med den här bilden är att man ser effekten av steget först dagen efter. Att den här toppen på, det här är ammoniumnivån då vid en punkt ut från IFAS-reaktorn och ut från, det kallas för S-utlopp. Och det som man ser är att toppen syns först dagen efter. Så vi har ett långsamt system där det finns en fördröjning, och det gjorde det lite extra komplicerat att implementera en styrstrategi. Jag gjorde också ett steg där jag ökade från syrenivån från 2 till 4,5 mg per liter. Och såg då också en tydlig förändring i kvävenivån, alltså syrebörvärdet eller syrehalten i reaktorn gjorde stor skillnad på hur stor ammoniumkoncentration som släpptes ut från systemet. Men det var ändå tydligt att det finns en fördröjning i systemet. Det är först dagen efter som man ser en tydlig förändring av det här steget som har gjorts. Och det är också väldigt tydligt att det finns en dygnsvariation i ammonium. Det är inte en rak linje, det här ammoniumkoncentrationen, utan den går upp och ner för varje dag, och det beror ju på inkommande ammonium från staden, hur när folk använder toaletten och så vidare. Och det gjorde att vi valde att använda oss av ett dygnsmedelvärde av ammoniumkoncentrationen vid en viss punkt istället för att använda den momentana mätningen. Och de här stegsvaren då som jag gjorde ledde inte till något tydligt, ett sådant stegsvar där man kan mäta stigtid och översläng och dödtid och sådana saker som man behöver för att trimma en regulator. Så det var inte ett alternativ att använda en PI-regulator till exempel. Så vi tog fram en egen algoritm för en regulator som vi kallade för en tidsdiskret integrerande regulator. Den här regulatorn har bara en regulatorparameter. Ett alternativ var att kunna använda en PI-regulator som har 2 parametrar. Men då hade man behövt trimma den och väga de här parametrarna mot varandra. Men vi valde vi skrev en algoritm för en som bara behövde en regulatorparameter. Och som överordnad styrstrategi så valde vi att använda en ABAC, en ammonia-based aeration control. Där man lägger till en yttre loop ovanpå den inre loopen som redan existerade. Så det här med att syrehalten förs in i en regulator och reglerar luftningen, den regleringen finns redan på reningsverket. Men det som lades till var att syrebevärdet istället för att vara konstant, alltså det här syrebevärdet, istället för att det var konstant så regleras det nu med hjälp av ammoniumkoncentrationsmätningar. Och algoritmen för den här integrerande regulatorn ser ut på det här sättet. Man tar den dagliga förändringen av syrebevärdet beräknas som reglerfelet, skillnaden mellan R-värde och bör-värde, och multipliceras med en faktor, KI, som är den integrerande förstärkningen. Och den faktorn kan man välja värde på och på så sätt välja hur snabb eller långsam den här regleringen är. Nästa steg är att göra en min-max-begränsning av den här förändringen. Den får max vara 0,5 mg per liter har vi satt den till. Så att den får gå plus eller minus 0,5 mg per liter vid varje uppdatering av koden. Och vi har också satt att uppdatering av koden sker endast en gång per dygn. Och det förklarar att vi har kallat den för tidsdiskret. Istället för att den är kontinuerlig och uppdateras ofta så uppdateras den en gång per dygn. Det nya syrebevärdet beräknas som gårdagens syrebevärde plus den här förändringen. Så det här, den här integrerande delen kommer in. Och sen därefter så finns det ytterligare en min-max-begränsning där vi sätter att syrebevärdet får variera mellan 2 och 5 mg per liter. Man vill inte att det ska gå lägre än 2 för då får inte de här mikroorganismerna tillräckligt mycket luft. Men man vill heller inte att det ska över 5 mg per liter för att vi gjorde ett test där vi såg att det var det maximala som blåsmaskinen i IFAS-processen klarade av att upprätthålla. Och att vi satte de här min-max-begränsningarna gjorde att vi fick en anti-wind-up i systemet. Så att det inte kunde bli så att om syrebevärdet låg mot en av de här min- och maxgränserna att det blev en wind-up i systemet, utan för varje ny beräkning så används tidigare beräkning och inte ett värde som kan ligga under 2 eller över 5. Den här regulatorn implementerades sen fullskaligt på verket den 24 april och sedan dess så har vi testat 2 olika värden på den här integrerade förstärkningen. 0,1 och 0,2. Så antingen så tog vi 10% av reglerfelet eller 20% av reglerfelet och tillade till gårdagens syrebevärde, så det är det som blev effekten. Och här är en bild på hur det såg ut när den här regulatorn testades. Syrebevärdet går ett steg ner för varje dygn vid midnatt. Det är då som den här koden uppdateras. Och den tar de här stegen neråt eftersom dygnsmedelvärdet av den här ammoniumkoncentrationen ligger under det börvärdet på ammonium som vi satte i regulatorn. Och den tar ganska små steg neråt. Det här är ju en typ av försiktig styrning att vi har tagit ett litet värde på den här regulatorförstärkningen. Integratorförstärkningen. Och när vi testade med 0,2 så fick vi tydligt större steg för varje dygn i syrebörvärde. Som både berodde på att förstärkningen var större men också på att det var en större avvikelse mellan det faktiska värdet och börvärdet. Och det berodde på olika driftförhållanden i verket. Och slutligen så valde vi valde att använda den mer försiktiga styrningen att använda framöver då på reningsverket. Tack så mycket för mig.
Tack Sanna, tack så mycket. Jättefint, bra jobbat. Titta, fina bilder också.
Ja, jag tog lite tester för att göra lite stickprover här.
Superbra,
Okej.
superbra. Frågor till Sanna? Sanna, hur var det för dig att vara ute på reningsverk och för att få lite insight där direkt på plats?
Men det var häftigt att få göra de här riktiga fullskaliga. Det fanns ju ingen modell att simulera i eller liknande. Så om jag ville testa vad som hände när syrenivån var hög så var det bara att ställa in hög syrenivå och se vad som hände på riktigt. Eller vad händer om man ökar flödet? Då fick jag öka flödet på riktigt och se vad som hände. Så det tyckte jag var väldigt spännande. Att avsaknaden av simuleringsmodell gjorde att alla tester som jag gjorde blev fullskaliga tester. Och sen så var det ju väldigt häftigt att få implementera den här regulatorn aktivt. Så att den körs ju nu då aktivt med den här regleringen som vi tar fram under projektet. Så det kändes som ett spännande resultat att komma fram till. Liksom.
Superbra, jättebra exempel. Hands-on projekt.
Verkligen.
Grattis. Thank you, Sanna. And we go on to Mel. And if you would like to share your presentation as next.
Hello, everyone. 1 second. You should see it now.
Yes. We see it in
Perfect.
full screen. The stage is yours, Mel.
Thank you. Hello, everyone. I'm Mel, and I will talk about my master thesis, targeted oxidation of pharmaceutical micropollutants in source-separated urine using the enzyme laccase, which I conducted at the SLU in Uppsala. A little bit background in the beginning. So urine contributes 79% of nitrogen, 47% of phosphorus, and 71% of potassium to the domestic wastewater, despite representing only 1% of the total volume. And this high concentration of macronutrients opens up the potential as a fertilizer and is a key motivation for source separation. Also, 64% of pharmaceuticals excreted by humans go via urine rather than feces, and the regulation of this gets more and more intensive, for example, with the EU directive. And source separation as a source control measure is a potential, but should not be the only reason to do the source separation, which we circle back to the nutrient content and the fertilizer potential. A little bit to the research. I did my master thesis at a research group at the SLU, which is looking at this topic. So source separation and safe nutrient recycling. And this got a real world momentum with the spin-off company, Sanitation 360. They collect at the Stadium Elida in Malmö and Studenternas in Uppsala human urine next to mobile collection sites at, for example, festivals. And this urine then is produced or processed to grand urine pellets, fertilizer pellets, which can be used for agricultural purposes. Pharmaceutical concentrations in urine-derived fertilizers are considered as very low risk for agricultural products. However, public perception makes addressing them a prerequisite for societal acceptance, which leads to my master thesis. The goal of the thesis was to find an enzymatic method for pharmaceutical removal in source-separated urine compatible with nutrient recovery. Chosen for that was the enzyme laccase, because it has a broad substrate range, which was also assessed for other studies before in other matrices though. So this is the first study where laccase was used in the urine matrix, to my knowledge. It is an established industrial use, which makes it commercially available and is using oxygen as a sole co-substrate. Yeah, the research questions I tried to answer were under what pH, temperature, and matrix conditions can a sufficient laccase activity be maintained? Can laccase degrade selected pharmaceuticals in urine over 24 hours, which was the period of my final pharmaceutical trial? And does addition of mediators like cyngaldehyd or vanillin affect degradation? Short view of the methodology. I conducted all experiments in pooled human urine, which was acidified to a pH under 3 with sulfuric acid. This is necessary for the later step of production of fertilizer to inhibit any microbiological processes. The activity in all experiment was assessed with an DMP assay, which gives a unit of activity per liter, just to have in comparison how the enzyme is working. And the enzymes used were one commercial laccase and one lab-grade T-versicolor laccase for the final experiment. It was 3 phases. Phase 1 was a condition experiment where I just look at the broad range, pH, temperature, concentration, oxygen, and acid type. I used the commercial laccase for that, and for the acid type, I looked at 5 different acids for acidification, and the only one which showed lower activity was acetic acid. That's why I just stuck to sulfuric. Phase 2 was then the validation for the final experiment. So dose finding, setup validation, and a 24 hours activity profile. And last one was the real pharmaceutical degradation trial, in which I spiked 19 pharmaceutical compounds to urine with a concentration of 50 micrograms per liter and treated it at 50 degrees for 24 hours. And I had 4 composition, 1 control without any addition, 1 laccase only, and 2 with mediators. So each mediator is 1 condition, in 4 in total. And all samples taken were analyzed with a mass spectrometer, UPLC, MS. So phase 1 results. You can see here the activity is given again in U per liter with the assay. And the enzyme showed a broad pH optimum from around 5 to 8. For the following experiments, I did a compromise between acidifying the urine or stay in acidic range, but also have an immediate activity with pH of 4.5, which were used for all other experiments. Then I looked at the temperature and looked at temperature optimum. This was found at 50 degrees. After that, the enzymatic activity is decreasing. Also, I looked at different concentration factors of the urine. For the process of fertilizer, the high water content of almost 95% has to be reduced. And this gives a concentration factor. It basically is initial urine mass divided by the urine mass after evaporation. And you can clearly see that with increasing concentration factor, the activity drops significantly to concentration factor of 9, where no activity was present anymore or not be detected. Last one I want to show you is a small oxygen experiment. It just shows clearly that with addition at this time point, you can see it with the red line of laccase, the oxygen content in urine drops significantly. This means that endogenous organics are oxidized by laccase, and just showed that this has to be met in a final setup. So aeration is necessary if you want to use laccase in urine. Which leads to phase 2, the validation of the final experiment. You can see here in the picture the setup for my final experiment. This is an oil bath where all sample bottles were inserted to keep in temperature. And on top of the bottles, you can see a small aeration device. These are plastic tubes connected to each bottle. And these plastic tubes were connected to an aquarium pump to keep constant aeration. And both temperature and aeration distribution was checked to be even over 24 hours. Next to that, I did an activity profile because now I changed the laccase from the commercial laccase to the T-versicolor lab-grade laccase. And you can see clearly that with the heat comes a trade-off. So in the beginning, we have a steep increase of activity with the heat, but also an drop of activity over time because of the heat inactivation of the enzyme. But this trade-off seemed mostly positive in the beginning, and the activity in the end is almost the same as the control you can see in the darker green, which stays constant over 24 hours. For the phase 3, the pharmaceutical degradation trial, so we had partial degradation observed for 5 compounds, including irbesartan and diclofenac, both priority compounds after the EU directive. And no clear laccase effect observed for several compounds. Possible explanation there is just structural resistance to direct laccase oxidation. This was expected for some pharmaceutical compounds, though several compounds were uninterpretable due to matrix interference in the control, which just shows how complex the urine matrix is. And the absence of effect in some pharmaceutical compounds, which were tested before in other studies, for example, in wastewater matrix, and showed degradation by laccase. So the absence of the effect here may reflect more on the urine matrix inhibition or also the analytical interference rather than true structural resistance. So the mediators provided no consistent enhancement. The pharmaceutical compounds which were oxidized by laccase only were also oxidized with mediators and vice versa for not oxidation. Now, from proof of concept to practice, this master thesis was a proof of concept. So we could oxidize pharmaceutical compounds with laccase in real source separated urine under storage compatible conditions, which makes laccase a compatible partner for nutrient recovery goals. Next steps within the research group will be urine metabolomics. This is ongoing at the moment. So this means just is laccase preferentially oxidized androgenous organics over pharmaceuticals. Also an enzyme mixture, so a mixture of multiple enzymes to broaden the compound range will be assessed, and an immobilized system for improved stability and reusability. And to come to my last slide, which should give just an outlook in the future. So this is the current process of fertilizer production of sanitation 360. And there we could include a possible step of microremediation with enzyme or enzymes to reduce the pharmaceutical load in the final fertilizer product. Yes, and with that, thank you for your attention.
Thank you, Mel. Thank you. Really interesting to see what you can do, what is in urine and pharmaceuticals. Very interesting research you are into there. Any questions? Roger?
Yeah, just a quick question. If I understand correctly, this laccase addition wasn't able to completely remove all the pharmaceuticals added. Is it not? How about just increasing the concentration of laccase that you add? What's the problem with that?
So firstly, I have to add this was a proof of study. So the real goal was just to show that laccase can work in urine, and I was quite happy to have also positive results in the final product. So for sure, you can increase the activity. Also, I should add, I used free enzymes. So in the future, you could also use fungal pellets, which produces the enzyme in the matrix itself in situ, which would also increase the concentration of the enzyme in the matrix over time. I reduced it with the urine because they are inhibitors in the urine. And also other studies showed before that laccase has a broad range of pharmaceuticals compounds, what I stated. So even though I couldn't see degradation of pharmaceutical compounds, this should still be seen not as a failure, but we know laccase can oxidize other pharmaceutical compounds as well. Only urine as a matrix is just really, really complicated to work with. Yes, and it will be interesting to see how it will develop over time.
Thank you.
Thank you. Thanks again, Mel, for being here and presenting today. now we go on to Saroj. If you could share your presentation about, you will tell us more about what it is. You are still muted.
Can you see my screen? Yeah.
Yes.
Yeah, I will like to start. So my thesis was modeling fate and transport of pharmaceutical in Lake Mälaren, and this work was carried within water engineering program in Uppsala University. First, going with the background, and Lake Mälaren is one of the important drinking water source for different regions along the catchment area, and strong treatment plant pathways where the treated wastewater is continuously flowing into the Lake Mälaren through different river and tributaries, and pharmaceutical is one of the compound that goes into the Lake Mälaren from different rivers and mix into the Lake Mälaren. And it is one of the rising environment concern is different aquatic plants and even human health are deteriorating through it. And this is also an interesting topic as European Union for Wastewater Framework Directive as developing a new regulating rules for those micropollutant like pharmaceuticals. It's going to the aim and objective. The basic aim of my thesis was to model the fate and transport of pharmaceuticals in Lake Mälaren from different wastewater treatment plant, along with the 3D lake transport model, the hydrodynamic 3D lake model. With the aim, there were main 5 objectives. First of all, I compiled different treatment plan data along with those flow, population equivalent and all. And second was to estimate the emission of different pharmaceuticals through the simple treat. Again, the third one, to implement the different tracers and a different degradation scenarios in the lake model to find the spatial and temporal pattern, how these pharmaceuticals are spreading along the lake model. And this presentation mainly focus on method when finding and how the framework can support the monitoring and water quality interpretation. As going to the study area, this one is the Lake Mälaren model, along with the different wastewater treatment plant. Like there were 53 different treatment plant, but we did with the 22 model treatment plant, along with the 7 receptor side, 4 on the different water intake side, and 3 on the water intake side, and 4 on the different basis side, along with the analysis period of 2013 to 2016. And those selected locations were used as a receptor just to compare the source from the source connected western side and to the eastern side of those Lake Mälaren. And going to the workflow, there was 2 different parts. One was the simple treat estimate, and the one was the 3D lake model. For the simple treat estimate, the different pharmaceutical data, along with the different treatment plan data, with the flow, P, and the compound properties like ionization and all, were used to find the load in the different treatment plant along with the different pharmaceutical compound. Again, in the part 2 with the 3D lake model, the different tracers along with the different degradation scenarios were implemented in the lake model to observe the dilution, decays, and how they are behaving along the lake model. So we'll get a final spatial pattern along with the different source and all. Just wanted to say that simple treat just tell us how much the pharmaceutical compound enter the lakes, and the lake model will just say how and where it goes, like how it transport along the lake. As the result from the simple treat, there was some dominant compound and there was some dominant treatment plan. This was mainly due to those for the low pharmaceutical. These were mainly due to the compound properties. Yes, the metformin is dominating, and along the different treatment plan, the Uppsala is dominating mainly due to their population equivalent and their discharge and all. For the pharmaceutical compound inventory, there were 183 different pharmaceutical compounds that were used, along with the 22 different treatment plant, and these load were later used to scale the tracer in the lake model. Now for the 3D PyGate lake model, it consists of 3D hydrodynamics for the circulation, stratification, mixing, and dilution, along with the 20 different vertical layers. The FABM is used to inlet the pharmaceutical tracer variables and a different decay behavior in the lake model, along with the 22 sources and a 5 different persistent group, which gives us 110 different tracers in the lake compound. And the analysis was done in between 2013 to 2016. Initially, it was run for 2010 to 2016, but 3-year period was taken as an spin-off period. And for those compound, these different 5 example compounds were selected just to separate the different persistent scenarios. Fluoxetine with a fast decaying rate with a half-life period of 15 days, ethanol, erythromycin, clarithromycin, and lamivudine within highly persistence, within half-life period of 722 days were selected just to know how these compounds are behaving in the Lake Mälaren. Just to know that persistent controls just how far the signals remain in the Lake Mälaren, and persistent just control how the source magnitudes are in the Lake Mälaren. Before analyzing the spatial pattern, we did a hydrodynamic validation. For hydrodynamic validation, those model temperature profile were validated with the absolute temperature profile that were measured in the Lake Mälaren. And we can see that there was good performance along with the depth of 0 to 10 meter with an RMSC around 1.85, but it was some uncertain going to the depth from below the 10 meter. For this validation, we consider the nearest model cell with a plus minus 2 days and interpolating the sampling depth of SLU with the model depth using ZCT. This one is the spatial concentration pattern. We got it from the scaling after the simple treat and a lake model, and we can see that different 2 compound, fluoxetine as a fast degrading compound and lamivudine as a high persistent compound. We can see that the source connected western side has a high concentration, and downstream side this has low concentration. For the fluoxetine, as this was mainly due to a distance, dilution, and basin exchange. And for those lamivudine, we can see that even the lower downstream showing some signals as they transported from the western side to the eastern side. As from this, we can get that Lake Mälaren behaves as a connected basins, not only as in one mixed lake. As going through the model result for the temporal behavior and source influence, we considered as one of the drinking water intake side, one bucket, and we can see that the compound, like highly persistent compound lamivudine, showing some signal, and there's the fast degrading compound like fluoxetine. These are seeing some certain peak. This is due to the persistent effect, like those highly persistent compound like lamivudine, they're spreading and they transport some distance, and they're seeing at the urban market, which is more to the eastern side, far from the western source connected side. And at that side, that the ocean brood was one of those dominating treatment plant, and this was also due to the source connecting issues, not only by the load ranking, like the different pharmaceutical travels from the source connected side to the different intake. And these the peak in these are not the pharmaceutical that we use. These are just so that how these different compound are at a different in water intake side, as we just use the constant input. As finally going for the applicability for the different water management VA cluster. This one is important for different monitoring design, source interpretation, and scenario testing. Like we can identify where the model signals and higher signals are there in Lake Mälaren. Maybe we can use as a source strength for different hydrodynamic connectivity, and we can also read the persistent behavior. And further, in future, we can use it in scenario testing and different treatment upgrades and different compound prioritization in different treatment plan. As boundary of this interpretation, these are just a scenario-based treatment, not just of direct the field measurement and the drinking, and also not our drinking risk assessment, and just a take-home message that pharmaceutical transport is controlled by source strength, source position, basin connectivity, and persistent. Thank you.
Thank you very much, Saroj, and thank you for being here as well and presenting. So from pharmaceutical reduction, previous presentation, to pharmaceutical loads in Lake Mälaren. Any questions to Saroj? I looked at basically that you used data from 2013 to 2016. Do you have any idea how the situation would look like if you would remodel today or in the future, let's say 10, 15, 20 years? Because yeah, these are a lot of different pharmaceutical compounds. They are changing basically with time, and we have seen that some of them are very persistent. Are there any trends, or how do people look at it? And also, I think it's very difficult to actually have all these pharmaceutical compounds analyzed one by one or in a package. There are other methods like looking into the health of the lake, basically qualitatively. How does it look, the ecological health, how the toxicity of the lake looks like? And what do you think about in general? Is this difficult with working with pharmaceutical compounds in this way?
Yeah, basically it was difficult to do with all those pharmaceutical in Lake Mälaren. So we just classified into different group how they are behaving with their compound properties, so that it will be easy for us to do, or just to classify which group they are in and which group they fall in. So it will be easy just like that.
Thank you for the interesting work. And this is very, very important because Lake Mälaren is one of our biggest, if not the biggest, raw water and drinking water resource in Sweden. I will stop the recording now.